Alright guys, so what we got to talk about in this video is how to deal with an infinite series in calculus. We are going to look at what a series is and how do we determine if it converges or diverges. So it's along the same lines of what we dealt with the sequences. So the first thing we need to know is what a series is. Specifically, what we're dealing with now is an infinite series, but a series in general is a collection of numbers added together. So it's the numbers that you got from a sequence added together. Okay, so you're given a rule just like we were with a sequence. You find a bunch of numbers and then you add them together. So this sigma here, this symbol, represents a series. So starting n value on the bottom and then the ending n value on top. So with an infinite series, we're going to infinity. Now there are series that are just, they stop at a number. So like if a 5 was up here, you'd plug 1 through 5 in and then calculate that. In an infinite series, it's a little bit different. So if we remember this from the sequence homework that we did, a sequence that converges has the nth term converging to some limit. So we took the limit as n approached infinity for our rule of the sequence, and if it went to some number, then we had a converging sequence. If it did not, then it went to, we had divergent. So a series that converges has the sum of its infinite terms converging to some limit. So we're going to take a look at that here in a second. We need to remember some rules here, and they're pretty similar to what we've done with integrals or any other really notation that we've looked at in calculus. But the first one, you guys can look over these. We have a constant times some rule. So we can pull the constant out and then run the series. If we have two series together, then we can treat them separate. And same thing with subtraction. So it usually makes it a little bit easier on us. The big one here, the one we really need to remember, is if the series converges, then the sequence converges to 0. Okay? So if we find that the series converges, we can say that the sequence converges to 0. Alright? The nth term test, that's what we're doing. That's going to be our first move for the next unit and a half. We're looking, nth term test is just running that limit. We're going to infinity. Okay, limit to infinity. So if the sequence does not converge to 0, then the series diverges. So pretty simple. So if we run the nth term test, we run the limit of our rule, and if we don't get 0, then we know that the series diverges. If this sequence converges to 0, then we can say that it possibly converges. So that's the big thing. That's the difference between a sequence and a series. We have to run some other test, which we really don't know yet, but we will get into a few over the next few videos, over the next week or so. We're going to learn quite a few different tests that we can use in different cases. So the nth term test is the first thing. We're really testing to see if it diverges. So if it diverges, we're done. But if we do get that, if we get to 0, then we can say it possibly converges, and then we have to decide what our next move is. But we're going to get into more of that a little bit later. So let's try a couple examples here, and then I have one other topic for this video that we need to discuss. So we have a series from 0 to infinity, 4 to the n. So we're going to take the rule 4 to the n, and we're going to run the limit. So limit as n approaches infinity for 4 to the n. Well, if we plug in infinity, 4 to infinity would be infinity. Okay, so not 0. So we can say that this is divergent, or diverges. Okay, so we get infinity. So as soon as it's not 0, we can say divergent. Next example, same thing, taking the limit as n approaches infinity. So we get 1 over infinity, which would be 0. So this possibly converges. So that's what we got to write. So from here, until we know other tests, this is what we're going to say. We're just going to say possibly converges, or possibly convergent. Okay? So again, anything but 0, we say diverges. If we get 0 for the limit, then we are possibly converging. All right, so let's take a look at one of the special series that we're going to take a look at this semester. So we have this thing called a geometric series, and it's written out like this. A geometric series, we have some ratio, some number raised to a variable power. So r to the n, that would be a geometric series. And a is just some value out front, some constant, okay, that we can deal with. So for example, if I had a 1 plus 1/2 plus 1/4 1 plus 1/8, we can say that this is geometric because we are increasing, we're multiplying each value by 1/2. So if we're multiplying by some ratio every time to get the next number, that's a geometric series. And the formatting is this, so we need to remember the formatting. Okay, so really we're talking about kind of like an exponential equation here. All right. So the good thing is if the r value is greater than 1, so if we are multiplying by some value that's bigger than 1 over and over and over again, then we know that it is going to be divergent. Okay, so absolute value of r, because if we're multiplying by positive 2, we know it's getting bigger, too big. Okay, and if it's a negative 2, we know it's still getting too big, but in the negative direction, but it still diverges. Okay, if the r value is less than 1, so in the example up here, the r value would have been 1/2. We're multiplying by 1/2 over and over again. We know that this converges. We can definitely say it converges to a value. Okay, it's not possibly convergent. We know it converges if the r value is less than 1, the absolute value of r. And the cool thing is we do know exactly what the series would converge to. Okay, we know the value, the outcome of this. So it's listed by a over 1 minus r. So the a value is that number out front, that constant, and then the r value again is that ratio that we've been multiplying by. So it's the number raised to the variable power. So let's go ahead and take a look at 2 examples here, and we can wrap this up. So series from 0 to infinity of 5 over 3 to the n. So first and foremost, it's important to see that this is in this format. Okay, we just might have to rearrange it a little bit. Some of us can see it right away, we might have to rewrite it. So we have, I'm going to rewrite it real quick. And I'm going to kind of ignore the, actually it's not going to be equal. I'm just going to rewrite this part. So this is 5 times 1 over 3 to the n. And really, this 1, we could say that's to the n too, because if we raise 1 to a power, it doesn't really matter. It's still 1. So now we can go ahead and rewrite this as a 1/3 to the n. Okay, we can use our power rules. So we have this. So this is definitely in this format. A would be 5, R would be 1/3. It's to the n power. So we can go ahead and take and plug into this equation. We can say that this 1/3 is less than 1, so we know it does converge. So we can write converge. Converges. Oops. And we can say what value it goes to. So A over 1 minus R. So 1 minus 1/3. That would be 2/3. So 5 divided by 2/3. Flip and multiply, we get 15/2. Okay? So the series, the infinite series, adds up to a number. It's kind of crazy to think about, but we saw in sequences where we have an infinite number and it does converge to some value. But we have an infinite number of numbers here that are adding up to some value. It's kind of crazy. All right, so let's take a look here. This next one, we have another geometric series. We have a 1 out front, which is the A, okay? 5/3 to the n. So our R value is 5/3. So the problem here is our R is greater than 1. 5/3 is bigger than 1, so we can say that this diverges. Okay? Diverges. Okay? So let me know if you have any questions on this. There are some tricky problems here, and we're going to get into a lot more different types of series as we go through. So let me know if you have any questions.